可以看上去。OK。Okay, now we move on to the second stage. So we have already a problem, number 6. And I think every group have to sign your name on the board. So the reporter, reviewer, opponent, please sign your names on the board. Okay, thank you. Okay, so we have 5 minutes to prepare, right?
feed a non-magnetic metal rod or ferromagnetic rod into the inductor coil. How do we obtain the magnetic and electric properties of the inserted rod with the circuit responses? This is a problem definition. First, for the non-magnetic metal, we chose aluminum, and for the ferromagnetic metal, we chose iron. Second, for the properties of the inserted rod, we want to know more about the conductivity. This is our device. First, the waveform generator, and then the oscilloscope, a 634 turns coil, a 6650 ohms resistor, and 2 probes, and also 2 metal rods, one aluminum, one iron, and both of them have a radius of 0.5 centimeter, and the length are both 13 centimeters. The circuit was connected as the left one. For channel 1, we have the source voltage, channel 2, we have the VR, and for channel 1 minus channel 2, we use the function of the oscilloscope to get VL. By observing the inductor's voltage of the hollow coil under different frequencies, we obtain this graph. As you can see right here, as the frequency increases, VL started to increase, but after a certain frequency, VL started to decrease as the frequency increases. The hollow coil has both the property of the inductor and capacitance, and can be seen as a parallel circuit, as I do right here. And using the two formulas at here, we can know that as omega squared equals 1 divided by LC, LC resonance happens, causing the current in VR to be emitted. Since the coil has both the property of the inductor and capacitance, we wanted to use power to further investigate the problem, because the inductor and capacitance don't together. Okay, and here's our theory. First one is about the magnetic field. The formula of the magnetic field can be written as B equals mu H, where B is the magnetic flux density, mu is the permeability, and H is the magnetic field intensity. For long solenoid, the magnetic field intensity can be expressed as H equals NR divided by N over N is in terms of the coil, Y is the current, and L is the length of the magnetic path. Therefore, B inside the long solenoid can be calculated as B equals mu and I divided by N over N. The second is about relative permeability. The relative permeability is the ratio of the permeability of a specific medium to the permeability of vacuum, which can be written as mu R equals mu divided by mu naught, where mu naught is the permeability of vacuum, which is 4 pi times 10 to the power of -7. The third theory is about eddy currents. Eddy currents are those of electrical currents induced within conductors by changing magnetic field in the conductor due to various law of induction. As you can see right here in this picture, we have an AC power supply right here, and it produces AC currents in the coil, causing a change in magnetic field. And a change in magnetic field will cause an eddy current right here on the conductor, and the eddy current will cause another new magnetic field, which cancels the original. The fourth theory is about the skin effect. In AC conductors, the skin effect means current concentrated near the surface and gets weaker as it moves towards the center within the conductor's cross-section, as you can see right here. It decreases as it gets into the center. The skin depth delta is defined as the depth where the current density is 1 divided by P, which is about 37% of the value at the surface. The formula of the skin depth can be written as delta equals 1 divided by the square root of pi F mu sigma, where delta is the skin depth, F is the frequency, mu is the magnetic permeability of the material, and sigma is the electrical conductivity of the material. The fifth theory is about the power dissipation of eddy currents. Under uniform material and uniform magnetic field, the power lost due to eddy current per unit mass can be calculated by P equals pi squared Vp squared V squared F squared divided by 6 k rho d, where P is the power loss per unit mass, Vp is the free magnetic field, and V is the thickness of the material, which is about 5 spin depth. F is the frequency, K is a constant, which is 1/4 in C. Rho is the resistivity of the material, and D is the density of the material. The sixth theory is about the hysteresis loss. The hysteresis losses are caused by magnetization and demagnetization of a core as current flows in reverse directions. A hysteresis loop shows the relationship between the material's magnetization and the external magnetic field of light. The frequency and the area of the hysteresis loop is proportional to the energy loss per unit volume of the material. As you can see right here in the picture, for the x-axis is H and and for the y-axis we have b. And the area inside the stage is proportional to the hysteresis loss. This is our main investigation. We want to calculate the power loss difference between free space and aluminum, and use the formula of power dissipation of eddy currents to get conductivity. For the power loss difference between free space and aluminum, we use E equals IR and P equals IL. And for the power dissipation of eddy currents, we use the formula that we just mentioned. However, because of the difference of phases between current and source voltage, because we still have L and C in the circuit, we wanted to use the data when LC resonance occurs, where the difference of phases is the minimum. Here are our data. So first it's about the power loss difference between aluminum and air. So first we use the waveform generator to generate a wave which has 90,000, which is 90,000 hertz, and we observe we are in the crystal, and then after some calculations, we have the difference between the power loss caused by eddy current of aluminum and air, which is about 2.87 microwatts. And then for the magnetic field, we use the formula E equals mu I divided by L. And notice that L is the length of the magnetic path, so it's not the length of the coil, but we assume it as twice of the metal length. Okay, and after some calculations, we can get B. And then it's the data of power dissipation of eddy currents. Again, we use this equation, and due to the effect, we only consider the mass of the aluminum, which contains most of the eddy currents. So the P loss can be rewritten as P loss equals P through L pi V squared R squared minus R minus V squared, where R is the radius, right here, and then L is the length of the rod. And then we inserted P and B, so some numbers that we just got, into this equation, and then we can get B. And then this is the data of skin depth. We use the formula delta equals 1 divided by the square root of pi sigma. And then after some calculations, we have delta. The magnetic field penetrates conductors about 5 skin depth, just as I mentioned. However, we got 16.5. So here we want to have a discussion about why we got 16.5, but not the number of. So we cut off 2 reasons. So first is about some other energy losses. So wire and other device might consume energy. And second, we didn't consider the difference of phases between current and source voltage. We did consider, but we did not accurately calculate. We only find frequency, which is around the frequency of the cell wave. So these are the 2 reasons why. And then, so we overestimated the power loss, causing D divided by delta to be overestimated. And then discussion for iron. We didn't calculate the conductivity of iron because the hysteresis loss is it's too difficult for us to get the pH graph. And the magnetic field was uniform due to the high permeability of iron. Maybe we can use some simulators or other ways to figure out this in future experiments. This is our conclusion. We compared the theoretical and experimental conductivity of aluminum with the value of D divided by delta, but we didn't get a conductivity of iron 62 coil. We can also use simulators to help us with estimating future experiments. That's all. Thank you.
Okay, question.
Okay, hello. I have several questions regarding your experiments. Well, first, I believe that we do not actually explain how your experiment works. So would you like to explain it a little bit? Because we don't really understand your you mention your setup, but you don't mention your experiment, and usually that is this is your setup. And so I want the detail about how you conduct your experiments.
Oh, okay. So just as I said, we first connected the circuit as this. So actually this is not this is the board, and this is the resistor right here. So okay. So we will change the frequency from there. So the waveform generator here with the waveform generator, and then it passes to the resistor, and then the coil, and then back to the waveform generator. And then we also use the oscilloscope to get the on and off. So this is, and then we have it right here, and then. But for channel 1, we have the source voltage, and for channel 2, we have.
So I believe it's probably better if you include your experiment detail in your presentation. And I would like to ask, does this show the current of this area? The current of your book, yes.
We use the oscilloscope to get.
Okay, time's up. So you have 20 minutes to prepare.
Good morning, fellow contestants and honorable jurors. I am the opponent from Team D1, and today I would like to oppose Problem 6, non-contact resistance. Well, first of all, the problem statement is like this. The responses of a LRC circuit driven by an AC source can be changed by inserting either a non-magnetic metal rod or a ferromagnetic rod into the inductor coil. So how can we obtain the magnetic and electric properties of the inserted rod from the circuit's response? And our focusing point will be on the conductivity and the materials of the rods. And to summarize the report from the reporter, they mentioned the phenomenon is that an AC source is differ by changing the different rods. And the theory is that magnetic fields and relative permeability, eddy current, which leads to power dissipation and also skin effect and hysteresis loss. And also the experiment, they focus on the power loss difference between aluminum and iron, and also the magnetic field and skin depth. Well, I'd like to mention some pros and cons of the report. Well, first, she has a very clear explanation regarding the theory variables, and they have clear demonstration of the theory, and also they have detailed demonstration of their devices. However, they lack the elaboration about the theory, about the certain points, and also the theory are separated. They don't mention how they're interconnected, and therefore can explain your experiments. And they fail to take enough energy loss and properties into consideration. And also, they lack the comparison between the experimental data and the theoretical data, which I believe is the most important in this report. And there are some of the points that I would like to consider during the discussion. Well, first is the phenomenon. I would like to discuss about how eddy current affect the experimental results. And also, they mentioned they have non-uniform magnetic field. And the big problem, I believe, is the quantification. I believe they do not quantify the results. And also the theory is about how the current oscillate and how can we infer from the oscillation of the current, since they mentioned that they use oscilloscope to measure the current. And also there's other discussion points regarding what is the most significant theory. Since they give so much information about their theory, I believe there is definitely one that is the most important. And also I believe they lack the comparison between the experiment and theory, which I would hope that they can elaborate more about that, and also the effect of different wave shape. And now I would like to invite the reporter on stage, and I will start to give several questions.
Yeah, also this bit.
Okay, so first, you mentioned that you don't have a uniform magnetic field, then how do you think that's going to affect your overall experiment?
Then that could change to.
Yeah, please.
For the uniform magnetic field, I mean for the iron, not for the. So the magnetic field was a uniform for iron because iron has higher permeability and it's around 200 times bigger than air. So first.
Well, I think you can also, I believe you answered this question pretty well, but I believe you can include the statistics into your report so the other can prevent the confusion. And you also mentioned that you don't get the DH graph, then I'd like to know the significance. Well, I don't really know the abbreviation, but please explain a bit more.
So this is I mentioned right here. So from the pH, from this pH graph, we can get the frequency and the area of the hysteresis loop is proportional to the hysteresis loss. So if I want to get a hysteresis loss, a good way to get it is to find the pH graph, but it's too hard for us to get it. So
then what are the difficulties, and how do you think you can overcome those difficulties?
Okay, so there are several the rods that we prepared are not big enough. So it's not, it's not big enough for the whole center core. Yeah. So the magnetic field will not be good.
Okay. Then, okay. So you mentioned about the oscilloscope, which is when we go back to the experiment setting, which you mentioned that it is used to measure the fluctuation of the current. Then could you please explain what do you see through that oscilloscope?
I get the source voltage and VR from the oscilloscope. So, okay, I can explain this more easily. So, right here, I can get the amplitude of the wave, and so, yeah, so I can calculate the voltage. But,
You mean a current? You can get the amplitude of the
yeah. But the thing that I want to mention is that we use so the VR right here is not what we just get from the oscilloscope. We divided it by the square root of 2 because we want to get the effective voltage. Yeah, because it's an AC source, so we divided it by the square root of 2.
May I use the fourth usage? Well, I believe in our RC circuit, the current, if you use the AC source, the current graph will be like, there will be certain damping because of the energy loss by the resistor. And do you observe any sort of graph that resembles this graph pattern?
You mean, but the waveform generator will always on, so like it kept on providing.
Energy. But I thought the whole point for the LRC circuit was and we also mentioned the eddy currents. Would you please tell me how the eddy current affect the experiment overall? Yes.
Okay. So the changing magnetic field will cause eddy currents, and then the eddy current will cause another magnetic field, which cancels the original current.
Yes. Then do you have a quantified results for how the eddy current cancel out the effect from the original magnetic field? Well, I believe that you can actually include more about the analysis of your data because this raw data is pretty hard for the viewer to see. So I believe this is some change that you can make in the future when you're trying to make a report.
I agree with that.
Well, it's pretty hard. Then,
I can explain it.
okay, please.
Okay, so this is the frequency, and we changed the frequency from the waveform generator. And the R was 6550 volts, and we get it from the like you can just see how big the resistance is. And then for VR, we get it from the oscilloscope. So we get the number first, and then we divided it by the square root of 2 to get the effective voltage. And then we divided VR by R, and then we can get R, so the current. And then we have the source voltage. We get the source voltage from the oscilloscope, and then we times I and the source voltage to get the source power.
Well, I believe in your presentation you also mentioned that you did not consider the difference between the current and source voltage, and I want to know how it is.
Okay.
And you say it's some potential thing that can ultimately affect your experimental result, and I want to know how it affects it, and what can you do to overcome such difficulty.
May I go to that?
Yeah, sure.
So just as I mentioned, because the coil also has the quality of the capacitance, so actually the whole system to look like this. So it has different phases, and then the DS, which is the total of all the three voltages. Yeah, so we can find the three voltages and the source voltage, but as you can see right here, so it's not like this. So
yeah, so there's an angle right there.
yeah, there's an angle right here.
And you do not consider each angle as a part of your experiment, right?
We did not calculate the angle, but we did consider it a little. So what we have done to make
What do you mean by considering a little? Because
okay,
this
yeah,
is something
I'm
that
explaining it.
okay, please.
Okay, so I just mentioned that. Oh, yeah, okay. So because we want to make the difference of the basis between the current and the source voltage smaller, so we wanted to use the data when LC resonance occurs. So when LC resonance occurs, it means that.
Oh, I'm sorry. You say LC resonance. So in LC resonance, the current goes like this, right?
You mean?
The current in the LC resonance in the oscilloscope, the pattern.
Or because it's like so it is R and then L and then when we have that's where it was 1 divided by LC in this situation because so in this situation, when we apply this inside, we found out that VL and VC0 have the same. So VL is as big as VC, but their directions are totally opposite, which means that they can cancel each other. And then.
Okay, I understand. I understand the explanation. Okay, so in your experiment, you only compared the aluminum and iron, right? Then do you think if you had in iron, the iron rod?
Oh yeah.
Yeah. So do you think if you insert rod of different sort of material, it'll affect the overall result? Like probably copper, probably carbon. Do you think? How do you think it's gonna affect the
Okay,
result?
time's up. So you have 1 minute for your conclusion.
Okay, so to conclude the previous discussion, I believe we talked about the eddy current effect on the result of the experiment, and we also talked about, I believe the most important thing right here is the quantification of the result. Because in a lot of part of her presentation, we don't see how the theory correlates to the overall result, and the quantification problem, I believe, is pretty important, and this does about that. And we also mentioned some of the difficulties she occurred when conducting the experiment, including the failure to get the pH graph, and also the ununiform magnetic field. And yes, and we also talked about how the current oscillate right there at the board, and also we compared. Well, I tried getting comparison between the experiment and theory, but obviously the reporter team do not compare the theory with their experiments, and the analysis of their
Okay, time's up. So the viewer, you have your floor.
Okay, so good afternoon. I'm the reviewer for problem number 6. And then, so I have some questions for the reporter since I want to clarify some things. And how can we validate your theory's correctness when you only have the data of aluminum?
So what we have done is that we compare d divided by delta. D divided by delta should be around 4 to 5, and we got this from a literature. And yeah, so.
And can I ask, is your theory suitable for both non-magnetic and ferromagnetic materials?
For the theory that I just introduced, it can only be applied for non-magnetic materials.
So when you put the aluminum rod into it, which factor, which number changes the most? Like you have many theories, and there are a lot of numbers in it. Maybe voltage changes the most, or maybe other frequency. I don't know. So I want to ask you, what changes the most and makes you think that it is aluminum?
So the result of air and aluminum will be different because of the conductivity, because aluminum is metal, and we can know that it's not because of the permeability, because the permeability of air and aluminum are the same.
Okay. So what do you think? What do you think is the standard or the number that changes the most? That can make me to see which material is the one that I put in. Do you think there is a main factor?
Well, I believe given the lack of experiment in her experiment group, we can barely tell the.
Yes.
Yeah, I agree with you.
I agree. And then, so you are not able to predict the material by your variable, right? Like
I mean, for ferromagnetic materials.
I think the problem statement is for us to say to find out if it's non-magnetic or ferromagnetic. So it's like no matter what we put it in.
Sorry, time's up. Time's up. You have 2 minutes to prepare.
I'm the reviewer for problem number 6, ground contact resistance. This is summary for the reporter. So she has a clear experimental setup and device and good schematic diagram, clear theory, and the setting of formula is explained. But there are some areas for improvement. First of all, no main focus through the problem statement, and then without the comparison between data and theory, because I didn't see any chart or something to the comparison between them, but they uses the theory's formula to do the data analysis. And then the lack of graphs, they didn't really have graphs to show the correlation between the data. And then they could use more materials instead of only aluminum or iron. And then results not quantified, just like what the opponent mentioned. And then theory impact could be normalized for analysis. This is my opinion, because if you want to see which is the main factor that is impacting this experiment, they can use normalization since they have a lot of numbers and factors. And then they could speak louder and more clearly. And this is the pros for opponent. I think he really understands the problem statement well. He asked a lot of crucial questions to the reporter and really good summary of the report. And then some areas for improvement is since the reporter's presentation is unclear, he cannot ask and discuss more deeply. And then some of the missed points that I think should be discussed is they need to talk more about how they conduct the experiment instead of a lot of theory and then lack of relation between or connection between why the theory and experiment are matching. And then they should try to change other methods to present the report. And then they had a lot of theory, but they don't have data to prove its correctness. So this is the question that the opponent asked, how the experiment works. And then the reporter says use oscilloscope to change frequency in order to measure voltage. And then the reviewer thinks that they need to explain more about it. And then another question is about non-uniforms, the magnetic field. And then the reporter said only in iron, but not in aluminum. And then the reviewer thinks that since they have theory, they have to explain it. And then difficulties of hysteresis loss calculations. And then the reporter says that the rock would be bigger to hold the inner coil. So oscilloscope measure fluctuation. And then the reporter says that measure amplitude of wave to calculate source voltage and measure the AC source. And then reviewer thinks that the wave function could be stated. So question, damping of AC since there is energy loss. And then the reporter's reply was unclear. So this is the question. Eddy current cancels original magnetic field. Any qualitative proof? And then the reporter doesn't have. And then reviewer thinks they should have theory. And then voltage different. Combine voltages with vector and not calculate the angle.
Time's up.
Okay.
Thanks. So, reporter, you have 2 minutes.
frequency where energy oscillate occurs to try to decrease the phase difference. The ferromagnetic rod is complicated to analyze. So in future work, we need to create a suitable model to figure it out. Maybe we can use some simulators to help us with this. And for the last one, we think we can try more different materials in future experiments.
So we have 5 minutes for any question from jury. Yes.
So the reporter takes up a lot of time to discuss many kind of laws. But the question of this one is that we can obtain the electric property and the magnetic property of the rod. So I have a question for you three. What is the most important property, electrical property and the magnetic property of this one? Which property?
So for us, we use permeability to get the conductor.
Yeah, so do you try to measure this?
I tried to measure the conductivity, but I did not get the permeability.
I also think that through their theory, I cannot see like a really clear relation between it. But since the problem statement has stated that we have to see the electric and magnetic property of it, so then I think they need to optimize their experiment setup to then we can know if there is a magnetic force to ensure that the magnetic property, and then for the electric property, we can go and measure the conductivity. Okay, so this is.
I mean, which property? What property we should take?
Jury say that you want to know what's the property in the magnetism of the electric. Can you mention that? Just don't repeat. Okay, make it shorter. What's the about statements that they mentioned that we need to measure the electric property and magnetic property. So what kind of properties? Can you give the examples?
Well, we should
Don't just follow the previous ones like electric conductivity. The new ones. Okay. Okay, maybe go to the opponent, then go back to you. Okay.
louder.
Louder,
Inductance and eddy currents and many other stuff that we can measure, and we can see the magnetic and electric properties.
Okay. Yeah, you want to get an answer?
I think I'm not sure about the answer, so
Okay.
Good.
Any question from jury? I can have one question, very short question. Because according to the statement, they mentioned the load, right? It's the load. They also calculation the load size, like a diameter or length of this load. It's the load, right? You mentioned you can have some parameter for the instant load, the family load.
So may you see that again? May you please speak louder?
Yeah, I mean, according to the questions, they say you will insert the load, like the aluminum load of the magnetic load. Do you also get some parameters for the load, like load diameter or length?
I measured the radius and the length, and
Did you change the parameter?
no, I did not.
Okay. Okay.
Do you
So-
think that, sorry,
Sure.
do you think that this geometry or the lens size is important parameter?
Yes, I think it might affect our results. So actually the rods we prepared aren't big enough, so that there will be some free space between the coil and the rod. And yeah, but for aluminum, I think that won't affect that much because the permeability of aluminum and air is similar. Yeah, but the eddy current will be.
So for your analysis, you only consider the skin gaps for the side surface, not these three side surface.
Oh, you mean like I can increase the length of the rod?
No, I mean in your you counting the power dissipation. You only consider the side surface, this boundary, the two sides you didn't consider.
No, I did not, because I think that's quite small, and I can ignore that.
Okay. Also the same question for the opponent. Thank you the answer. If you check the parameter for the load, anything or any important thing or critical ones you will expect.
You mean the solenoid?
No. The rod. Just a rod.
The rod. Yes, I believe there's going to be.
So what, for example, what's the impact?
For example, if you have the radius of the rod that is too big, the gap can actually influence. So you always want the geometry of the rod to be the same for all the rods, like metal rod or non-magnetic rod. You always want them to be the same in this experiment.
Okay, what's your answer?
I think using different materials of rods might cause different interactions of magnetic field. Okay, so that is my answer.
But okay, that's fine. Okay, we are ready. So we will take a score for the report. Okay, score for the reporter. 5, 4, 6, 6, 7. Okay, the score for the opponent. Opponent. Okay. 6, 6, 6, 7, and 7. And the final one for the reporter score. Okay. 5, 5, 5, 6, and 6. Okay, any question? If not, then we should